The very notion that celestial bodies in the night sky are distant worlds, akin to our own planetary arrangement, naturally spurred contemplation regarding the existence of planets orbiting them and the possibility of life upon these cosmic entities. However, theorizing is one thing, empirical discovery is quite another. Given that planets are significantly less massive and emit far less light than stars, their detection presents an immense challenge. Despite intermittent attempts, success remained elusive until the close of the 20th century. By the late 1980s, several observational techniques had achieved the requisite precision. Consequently, in the early 1990s, the era of discovering exoplanets commenced. Currently, we acknowledge the existence of several thousand such worlds, with their numbers steadily increasing. It has become evident that alien planetary systems and their constituents can exhibit profound deviations from what we observe within our own solar system. A vast cosmic expanse of exoplanets has been unveiled. Our subsequent task is to elucidate their formation, internal structure, and evolutionary trajectories. This present discourse delves into this, arguably the most dynamic frontier of astrophysics. We propose to focus our attention on a preeminent exoplanet known as Osiris, or more formally, the evaporating planet HD 209458b. Osiris resides within the constellation Pegasus at a distance of 153 light-years from our Sun. By classification, Osiris is a hot Jupiter, signifying a gas giant with a mass comparable to Jupiter's, yet orbiting its parent star at a considerably closer proximity than Jupiter orbits our Sun. Osiris possesses a radius of approximately 100,000 kilometers, or 1.35 times that of Jupiter. Its mass is 0.69 times Jupiter's mass. The orbital distance from its star is a mere 0.47 astronomical units, substantially less than the distance between the Sun and Mercury. A year on Osiris encompasses a mere 3 Earth days. The revelation of its atmosphere was facilitated by HD 209458b's distinction as the inaugural planet, for which an independent emission spectrum, disentangled from its star's radiation, was obtained. Within this spectrum, absorption lines indicative of sodium were identified. Subsequent investigations led to hypotheses concerning the extent, structure, and thermal characteristics of its atmosphere. The atmospheric envelope commences at a radial distance of 3.1 Jupiter radii from the planet's core. Osiris is an immense gas giant, replete with a diverse array of gaseous compounds. Its composition has been found to include hydrogen, oxygen, carbon, carbon dioxide, and methane, in addition to water vapor. At first glance, its atmosphere appears inherently stable. Estimates place the temperature of the lower atmospheric strata at 1,300 Kelvin, a level insufficient to overcome gravitational forces and allow molecules and atoms to escape into space. Nevertheless, it is understood that atmospheric temperature can fluctuate dramatically with altitude. The elevated temperature of the uppermost atmospheric layers is attributable to heating by short wavelength ultraviolet radiation emanating from its star. For Osiris positioned significantly nearer to its incandescent star than Earth is to the Sun, heating from the far ultraviolet spectral range of radiation is expected to be substantially more intense. Recent supplementary observations of the planet in the ultraviolet spectrum, conducted using the Hubble Space Telescope, have revealed that Osiris eclipses its star to a far more pronounced degree in the Lyman alpha emission line. The star's brightness diminishes by 15%, a figure consistent with the size of the hydrogen envelope surrounding the planet, estimated to extend approximately 4.3 Jupiter radii. Given that the Roche lobe, a region where matter is retained by a planet's gravitational influence, for Osiris is calculated to be 3.6 Jupiter radii, these observational findings can only be reconciled by postulating that the planet is continuously shedding material at a rate of approximately 130 kilometers per second. This rate exceeds the second cosmic velocity for Osiris. This phenomenon is directly linked to the planet's appellation, Osiris, named after the Egyptian deity who was dismembered by the god Set. Indeed, it is estimated that Osiris loses between 100 and 8 metric tons of hydrogen per second. This implies that over its estimated 5 billion year existence, the planet could have shed as much as 7% of its original mass. However, there exists a possibility that its magnetosphere, while operational, may mitigate this hydrogen loss. It is conceivable that Osiris's atmosphere is characteristic of planets orbiting stars similar to our Sun, at distances less than zero point 0.1 astronomical units. Yet, unlike its counterparts, Osiris is dissipating at an astonishing rate, effectively resembling a colossal cometary planet, trailing streams of various gases. At its current rate of evaporation, it is projected to be entirely disintegrated in 1 trillion years. We, of course, aspire to witness this remarkable cosmic event. Astonishingly, researchers have also discerned an extraordinarily powerful tempest on Osiris. This planet-wide vortex is a consequence of the significant temperature differential between the perpetually star-facing side and the far side, which remains in perpetual darkness. This disparity drives potent atmospheric currents. Naturally, researchers were unable to visually confirm these phenomena directly. Instead, they relied on sophisticated modeling. To enhance the accuracy of these simulations, astrophysicists incorporated a multitude of factors governing the interplay between stellar wind and the planet's atmosphere, including charge exchange between stellar wind and neutral atmospheric particles, their subsequent ionization, gravitational influences, atmospheric pressure, radiative acceleration, and the spectral broadening of emission lines. These intricate details collectively indicated the presence of carbon monoxide gales on Osiris, with wind speeds approximating 2 kilometers per hour second, or 7,000 kilometers per hour, with potential variations ranging from 5,000 to 10,000 kilometers per hour. It becomes apparent that achieving a gentle tan on this world is highly improbable. The fascination of astronomers with Osiris, leading to its designation as the immortal patron of the afterlife, can be attributed to its role as a pioneering discovery for the scientific community dedicated to the search for extraterrestrial life within the cosmos. While life on Osiris is demonstrably absent, any hypothetical inhabitants would face dire circumstances. This scorching, rapidly evaporating exoplanet was first detected in 1999 using the Doppler method. At that juncture, slightly over 30 planets had been identified through this technique, though its reliability was not universally accepted. A considerable number of astronomers hesitated to embrace this finding until another team of scientists independently confirmed the planet's existence using the transit method, thereby definitively validating the reality of these novel celestial bodies. Since then, Advancements in instruments for deep space exploration have continued. Furthermore, a significant leap in this and numerous other astronomical fields is anticipated with the deployment of the James Webb Space Telescope. While not solely dedicated to exoplanet detection, it serves as a successor to the Hubble Space Telescope, possessing capabilities that will undoubtedly propel advancements in the broader search for exoplanets, particularly those resembling Earth. The advent of future colossal telescopes, including the Giant Magellan Telescope, the 13-meter 30-meter telescope, and the European Extremely Large Telescope, promises capabilities on par with the James Webb. These instruments are poised to facilitate the discovery of a multitude of new exoplanets. More importantly, they will lower the detection threshold, enabling the identification of a greater number of terrestrial-type planets and considerably smaller celestial bodies, potentially even extending to the detection of exomoons. In essence, we inhabit a universe teeming with exoplanets. The number of confirmed planets now numbers in the thousands and is projected to reach tens of thousands within the next decade, as we augment both the quantity and observational power of our automated telescopes. Our initial remarkable discovery was made around the star HD 83443, specifically a novel exogiant. This newly identified exoplanet, characterized by perpetual storms, possesses a mass 1.5 times that of Jupiter. Its orbital path is defined by a semi-major axis of 8 astronomical units and an eccentricity of 0.76. A year on this planet spans 22 Earth years, rendering it anomalously frigid. The system encompasses 2 exogiants, each on distinct orbits. It is highly probable that this configuration arose from past gravitational scattering events, which rendered HD 83443b a short-period planet and displaced HD 83443c to its current wide orbit. It is also possible that a third exoplanet previously existed within the system, but was ejected. While the preceding celestial body is likely exceedingly cold, the climate of the subsequent exoplanet evokes a vacation paradise. Introducing 55 Cancri E, a planet that orbits its sun-like star so closely that it is perpetually engulfed in flames. The surface temperature on this world reaches 2,436 degrees Celsius. This exoplanet, situated 50 light-years from Earth, is classified as a super-Earth, a category of planets whose masses are several times that of Earth and bear no resemblance to any known world. The surface of this incandescent realm is blanketed in lava and perpetually ablaze. A year on this planet lasts a mere 18 hours, which is ample time for a substantial tan. Its gravitational pull maintains one hemisphere in perpetual daylight and the other in unending darkness. The dramatic surface temperature variations are attributed to potential volcanic activity, which releases vast clouds of dust that envelop the planet, impeding thermal radiation. Should the James Webb Space Telescope detect an atmosphere on this fiery world, and if oxygen or nitrogen predominates within it, the resultant imagery will depict the lava-covered surface of the super-Earth 55 Cancri E. We now journey onward to Gliese 667c, one of 3 exoplanets orbiting a red dwarf star of spectral type M. This star is located 22 light-years from Earth in the constellation Scorpius. The planet completes one revolution around its star every 28 days. The most compelling aspect is that this exoplanet resides within its star's habitable zone. Remember to pack an inflatable mattress, as we are likely encountering an ocean planet. It is highly probable that this world is subject to intense storms and phenomena associated with vast volumes of liquid and wind. Life on this planet, if it exists, would likely differ fundamentally from our own. Furthermore, its indigenous killer whales might prove remarkably aggressive, given that Gliese 667c is a super Earth with a mass approximately 3.7 times that of Earth, resulting in substantially higher surface gravity. A visit to this planet would significantly increase your weight compared to Earth, a fact that would undoubtedly be quite disheartening. Assuming the planet possesses an Earth-like atmosphere, its surface temperature would hover around 30 degrees Celsius. However, if its atmosphere were significantly denser than Earth's, it might resemble Venus, a far less comfortable scenario. Due to its proximity to its star, it is plausible that the planet is tidally locked, with one hemisphere experiencing perpetual day and the other eternal night. Evidently, the close proximity between the star and exoplanet causes the star to appear considerably larger in the sky compared to our Sun, likely manifesting as a red disk 3 times wider and 10 times greater in surface area than our Sun. Our fourth subject is TIC 1729098b, a planet orbiting 2 stars, discovered thanks to the Kepler Space Telescope. To date, only 14 such circumbinary exoplanets have been identified. These are also known as planet hunters because they orbit binary star systems, or stars that revolve around each other. This novel world is a gas giant comparable in size to our own Jupiter, but considerably more massive, boasting 2.96 times Jupiter's mass. It traverses its orbit over 200 days around 2 sun-like stars that, in turn, orbit each other. High-resolution near-infrared images have revealed a signal suggesting the potential presence of a moon orbiting the planet, likely twice the size of Earth, a veritable Pandora. We must certainly investigate this further. While moons are ubiquitous within our solar system, not a single one has been confirmed beyond its boundaries. It is theorized that the environments around cold gas giants situated at distances from their stars, analogous to the orbits of Jupiter and Saturn, are favored locales for their formation. The prevailing conditions on this satellite remain unknown. We now set course for the planet Kepler 1649c, located 300 light-years from Earth and only 1.6 times its size. This is a rocky world situated within the habitable zone. The planet orbits its star at a close distance, with a year lasting approximately 19 Earth days. Current data indicates that the planet receives 75% of the stellar light received by Earth. Its estimated equilibrium surface temperature is minus 39 degrees Celsius, so pack your warmest clothes. This planet is highly likely to harbor seas and oceans of liquid water. To date, no stellar flares have been observed from the star Kepler 1649. This is significant, as it is a red dwarf, a class of stars known for their volatile nature. The same system contains at least one other rocky planet of comparable size, but its orbit is situated nearly twice as close to the star. We can only hope for more comprehensive information in the near future. It is time to examine the extraordinary world of Gliese 1132b, located approximately 40 light-years from our Sun. This planet is 1.8 times larger than Earth and completes a full orbital revolution in a mere 1.6 of our days. An atmosphere has been detected on this exoplanet. This is particularly noteworthy as the planet orbits extremely close to its star and, by all calculations, should have lost its atmosphere long ago. The planet exhibits potential volcanic activity, evidenced by an unusually high concentration of hydrogen cyanide, up to 0.5%. It is also rich in hydrogen cyanide, methane, and ammonia. In certain respects, this planet shares similarities with Earth. They possess comparable densities, sizes, and ages. Both planets began with hydrogen-dominated atmospheres and were initially hot before cooling. However, as we observe, their formation histories diverge significantly. This example illustrates that not all terrestrial-type planets commence their existence like Earth, nor do they necessarily conclude as such. Some may originate as mini-Neptunes and subsequently evolve into Earth-like worlds through a mechanism whereby the star evaporates the primordial atmosphere. Finally, we arrive at the seventh and most distant world, M51b. This is one of the first officially confirmed planetary candidates discovered beyond our Milky Way galaxy. The exoplanet was detected within the hydrogen galaxy M51, situated 28 million light-years away. The exoplanet resides in a binary system, orbiting two massive objects that, in turn, revolve around a common center of gravity along with a massive companion star. The transit observed by astronomers lasted approximately 3 hours, during which the detected X-ray emission from the star dropped to 0. This allowed researchers to estimate that the object might be roughly the size of Saturn and orbit a neutron star, or a black hole, at a distance twice that of Saturn's orbit from our Sun. However, this distant exoplanet will not transit its star again for another 70 years, meaning a considerable period will elapse before astronomers can observe this event anew, and we, at best, will be elderly by then. We have, of course, only explored a fraction of the fascinating and captivating worlds, highlighting 7 in particular. We look forward with optimism to the future, anticipating that the next generation of telescopes will provide answers to all outstanding questions regarding exoplanets and naturally raise new ones. The James Webb Space Telescope is already operational. The Kelt telescopes are scheduled for 2023, the Giant Magellan Telescope for 2029, the Extremely Large Telescope for 2027, and the Roman Space Telescope for 2027. All these instruments are expected to commence operations within the next decade, ushering in a new era of observational capabilities. They will empower us to analyze the atmospheres of smaller exoplanets, obtain direct imagery, decipher microlensing signals for less massive planets, work with diminished radial velocity measurements, and, in essence, accumulate unprecedented statistical data. Most importantly, we may approach the discovery of an Earth 2.0. Simultaneously, we will continue to add more unusual and unexpected planets to our exoplanet collection. The motivation? Primarily scientific inquiry. Furthermore, we grapple with a fundamental question. Are we alone in the universe? Investigating the diverse array of exoplanets and planetary systems discovered to date, ranging from the diminutive to the colossal, and from those appearing Earth-like to the profoundly bizarre, not only enhances our understanding of how these individual systems formed and evolved, but also offers critical insights into the potential for life elsewhere in the cosmos. The Milky Way galaxy is a relatively average-sized galaxy. Within this galactic island, there may be as many as 100 billion planets. It goes without saying that the vast majority remain unexplored. It is highly probable that fully cataloging our galaxy, akin to tidying a closet in our home, will require hundreds, if not thousands, of years. Nevertheless, each confirmed exoplanet discovered by astronomers possesses its own unique characteristics and attributes, often deviating dramatically from what we are accustomed to observing. This uniqueness can manifest in various ways. Today, we will present two intriguing exoplanets that not only orbit their parent stars at extremely close distances, but over time evolve into something more. Considering our solar system, the planet closest to our star is Mercury, the smallest of the terrestrial planets, traveling at a speed of 47 kilometers per second at an average distance of 58 million kilometers from the Sun. However, this is far from a record holder in terms of speed and proximity to a parent star. This distinction is currently held by an ultra-hot Jupiter-class planet, TOI 2109b, exhibiting a record-breaking orbital period around its star in a stellar system located 855 light-years away. This planet completes its orbit in a mere 16 hours. Imagine you haven't even finished your day, and it's New Year's again on TOI 2109b, albeit with a burnt-out Christmas tree. It seems there's no one left to celebrate the holiday there. As the temperature on the day side is approximately 3,225 degrees Celsius, approaching the temperature of small stars, meaning any thought of a light tan is out of the question, as TOI 2109b is situated at a distance of roughly 2.4 million kilometers from its star. Moreover, this gas giant is tidally locked, and due to its extreme proximity to the star, the TOI 2109 system serves as an ideal laboratory for studying the process of tidal disruption of planets by stellar gravity. Planets that orbit their stars closely and whose stars are still on the main sequence of the Hertzsprung-Russell diagram, meaning they are undergoing thermonuclear fusion of helium from hydrogen in their cores. Consider the following example. Despite the prevailing scientific consensus that white dwarfs can host planetary companions, direct evidence to support this was previously lacking. However, quite recently, in the constellation Draco, at a distance of 80 light-years from us, an unusual white dwarf was discovered that is regularly eclipsed by its companion. A significant portion of the light reaching the dwarf, and subsequently Earth, is obscured. According to the discoverers, this companion could be either a Jovian-sized planet or, with considerably lower probability, a brown dwarf. These observational findings were further substantiated by data from the Spitzer Space Telescope. The compiled information conclusively established that a transit of the white dwarf WD156 plus 534 by a non-luminous companion of Jovian scale had been detected. This white dwarf itself is unremarkable. With an effective surface temperature of 4,500 degrees Celsius, it is considerably cooler than our Sun. This indicates that it formed approximately 6 billion years ago, predating our solar system, and has been cooling ever since. Its mass is approximately half that of the Sun, and its radius is about 75 times smaller than the Sun's, meaning it's only 40% larger than Earth. However, it's not entirely typical, as it's the outermost component of a visual triple star system. The inner components are red dwarfs. The companion of the white dwarf, designated WD156b, has a semi-major axis for its orbit of just 0.02 solar units. In other words, it's only 3 million kilometers from its star, which is 20 times less than the average orbital radius of Mercury. The radius of this body is just over 10 times that of Earth, making it appear quite colossal compared to its host star, the white dwarf WD 1856 plus 534. This explains the significant dimming of the dwarf's light that researchers detected. The orbital period of WD156b around the white dwarf is also known, lasting a mere 34 hours. Unfortunately, the precise mass of the companion planet remains unknown. Determining it requires knowing its radial velocity, which has not yet been established. Yet this velocity is measured by the Doppler shift in spectral lines, which is not apparent in this case. Nevertheless, we do have some interesting information. When comparing the results of visible light dimming observations of the dwarf, conducted with photometers from a giant telescope on La Palma Island, with similar observations in the near-infrared spectrum made by the Spitzer Space Telescope, it was discovered that the brightness variation dynamics in both ranges were nearly identical. This implies that the thermal radiation flux from the exoplanet is no more than 6% of the dwarf's own flux. Thus, such a faint body could be either a giant planet or a very low-mass brown dwarf. Subsequent analysis indicated that the mass of WD1856b should not exceed 13.8 Jupiter masses. This estimate is close to, but still slightly below, the theoretical lower limit for brown dwarf masses, making their candidacy unlikely. Based on the available data, it can be reasonably asserted that we are dealing with an incredibly large planet. But how can the companion WD1856b be only 3 million kilometers from the white dwarf? And how did it survive the death of its star? The fact is, during its transformation into a red giant, a star engulfs any of its planets that are too close. For instance, when the Sun does this in approximately 5 billion years, it will destroy Mercury, Venus, and possibly Earth. But how did planet WD156b survive? On its current orbit, it would have long since been incinerated. Researchers propose two plausible scenarios for consideration. The first, the white dwarf's progenitor star, before its demise, must have first transformed into a red giant, swelling to the size of Earth's orbit. If a planet existed closer than this, it would have been completely enveloped by the giant's outer shell. Immersed in hot gas, it would have lost its burnt-out outer layers, but could have retained its core. Moving through the gas plasma cloud, it would have slowed down due to friction and approached the star's dense core, which, after shedding its gaseous envelopes, transformed into a white dwarf. After the shedding, the planet would have found itself in gas-free space once more, settling into a stable orbit around the dwarf. If the red giant's shell shedding had been delayed, the planet would have continued to decelerate and eventually collided with the stellar core in a catastrophic event. In such a scenario, terrestrial astronomers would not have a surviving pair of a white dwarf and its companion, as the companion itself, whether a planet or a brown dwarf, would have been doomed to complete destruction. However, this scenario seems less probable because performed model simulations suggest that a complete shedding of a red giant's outer envelopes, followed by orbital stabilization of the companion, is unlikely due to several dynamical mechanisms. And here we move to the second scenario. These same simulations indicate that the progenitor star already possessed several planets in more distant orbits, and after its transformation into a red giant, their orbits lost their previous stability. As a result, planet WD156b gradually migrated to an orbit close to the dwarf, while any others, if they existed, were ejected into free flight along with their inhabitants across the cosmos. This restructuring could have taken approximately 1 billion years, which aligns well with the white dwarf's advanced age. It seems that's what happened, and at some point, the planet became larger than the star it orbits. Yes, space is undoubtedly an astonishing place, full of intriguing and even enigmatic phenomena and objects. Well, for the James Webb Space Telescope, which is still gearing up for operations, there is much work ahead, including the study of this remarkable pair. We hope it will help resolve the question of WD156b's origin. Interstellar space travel has long been a dream for many, but the technical challenges associated with such an expedition are extremely complex. The nearest star system is 40 trillion kilometers away. Using current technology, a journey there would take 30,000 years. That's an eternity. By then, even women would have grown beards. Yet even today, there are projects that allow for the construction of a spacecraft capable of traversing this distance in 30 years. How is this possible? And what will we discover in the Proxima Centauri system? That's what we'll discuss today. So let's embark on our long journey, just over 4 light years from Earth. The good news is that evidence for the existence of an Earth-like planet, Proxima Centauri b, has been confirmed, and it's located in the habitable zone of its star, Proxima Centauri. The discovery of this new planet was the result of long and meticulous observations under the general designation pale red dot. The star system has another planet, Proxima Centauri c, but it's too far beyond the habitable zone and resembles an icy Neptune more than Earth. A little later, using the espresso spectrograph on the VLT telescope, a third exoplanet of sub-Neptune size, Proxima Centauri d, was discovered around Proxima Centauri. It's closer than the first two planets. It orbits very near its parent star and is 10 times closer than Mercury is to the Sun. A year on Proxima d lasts 5 Earth days. The planet's mass is approximately 1/4 that of Earth. And the bad news is that Proxima d also falls outside the habitable zone, as a human would heat up to ignition in fractions of a second there. But let's return to a more comfortable environment and examine Proxima b in more detail. It was discovered using the radial velocity method, where periodic shifts in spectral lines caused by the Doppler effect allow for the detection of planets around a star. It seems we are very fortunate. Although with our current technology, traveling to this exoplanet would take thousands of years, even if a super-fast spacecraft were conceived and built. Don't rush to pack your spacesuits. To understand if conditions are suitable for existence on the planet, we first need to study the star it orbits. Proxima Centauri is a red dwarf and is nothing like our Sun. The star is much smaller and emits correspondingly little light. Proxima Centauri is only about 1.5 times larger than Jupiter, and compared to our star, its size is 7 times smaller. The entire stellar system is called Alpha Centauri. From Earth, the two stars appear as a single luminous object, Alpha Centauri A and Alpha Centauri B. The planet that has caught our attention for colonization orbits the third star, Alpha Centauri C, also known as Proxima Centauri. The star is quite dim, so we cannot see it with the naked eye, as a red dwarf emits a small amount of energy. Both stars orbit in common center of mass in an elliptical path, with a period of almost 80 Earth years. The gravitationally bound red dwarf Alpha Centauri C is located 0.21 light years, or almost 2 trillion kilometers, from its more massive and brighter siblings, and its orbital period around them is at least 500,000 years. Incidentally, for an observer on Earth, the angular separation between Proxima Centauri and Alpha Centauri will decrease fourfold in approximately 300,000 years to about half a degree. To receive sufficient warmth for life, a planet must be much closer to a dim red dwarf star. This is the case with Proxima Centauri b. It is located 7.5 million kilometers from its star. For comparison, there are a whole 150 million kilometers between the Sun and Earth. A complete revolution around the star Proxima b takes only 11 days. Such close proximity, on the one hand, allows for the existence of water, but on the other hand, it can be quite dangerous. Regarding water, it can only exist on the illuminated side, as due to tidal locking, the planet always presents only one side to its star. So, local orcas have to paddle intensely to avoid getting cooked. However, there's an opinion that a rare day-night cycle on Proxima b does occur due to its elongated orbit, as tidal influence from the star weakens at the extreme points. This means a day on this planet lasts almost 2/3 of its year, or about a week by Earth standards. But this is not the biggest inconvenience. Proxima b is threatened by a far more dangerous foe. Like many other red dwarfs, Proxima Centauri is a flare star. During flares, its luminosity can increase several-fold. Flares are accompanied by an increase in brightness, not only in the optical, but also in the X-ray range. For example, in 2017, the star's brightness increased 1,000-fold in just 10 seconds. This is 10 times brighter than the most powerful solar flares in a similar range. Over the planet's lifetime in the vicinity of such a volatile star, these events could simply blow away its entire atmosphere, if it has one, along with its inhabitants. Calculations also indicate that the planet's surface would be subjected to a large amount of extreme ultraviolet and X-ray radiation. Researchers estimate that Proxima b should receive at least 250 times more X-ray radiation than Earth. This imposes certain limitations on the possibility of life existing on the planet, as X-rays are ionizing, meaning they are harmful to living organisms. For instance, a lethal dose of radiation for humans is 5 to 10 sieverts, 100 to 1,000 sieverts for insects, 10,000 sieverts for viruses, and 10,000 to 100,000 sieverts for extremophile bacteria. This sounds horrific, of course. However, if the planet has a gas envelope with a density comparable to Earth's and a magnetic field similar to Earth's, organisms on its surface could survive most flares on Proxima Centauri. If the atmosphere is less dense, high-energy particle ejections would pose a threat to some species, such as soft-bodied humans. In the worst-case scenario, if Proxima has almost no magnetic field, flares would simply strip away its atmosphere, and then all Earth-like life would perish. Nevertheless, Proxima b hypothetically has a chance to retain its protective gas envelope. The fact is, this planet is slightly larger than Earth. Its mass is 1.27 Earth masses. But unlike our blue marble, it could not have formed from the protoplanetary disk so close to its star. Therefore, it is quite likely that the planet originated from those regions of the protoplanetary disk where there is a lot of ice. If so, it has more than enough volatile substances to maintain its gas envelope. It is also interesting that Proxima Centauri receives about 65% of the light from its parent star that Earth receives from the Sun. Therefore, it could be significantly colder here. We can only rely on the presence of an atmosphere. Thanks to the greenhouse effect, it would be quite warm here, with an average temperature of nearly a comfortable 7 to 15 degrees Celsius. Again, at such a temperature, the existence of the much-needed liquid water on the surface is possible. What about the possibility of any forms of life on Proxima b? There is hope for that too. Theoretically, life is still possible on the planet even with such powerful ultraviolet radiation flares. According to astrobiologists, some living beings can hide from lethal ultraviolet radiation by using natural shelters. For example, they can exist underground or deep underwater. Additionally, attention is drawn to another potentially possible form of life that can convert received energy into biofluorescent radiation of a different wavelength. This process involves special protective proteins that absorb harmful ultraviolet radiation. Astrobiologists provide an example of an interesting and very resilient Earth life form. No, not politicians, but coral polyps. Some species of coral polyps contain fluorescent proteins that are photoactivated when illuminated by ultraviolet light in the long wavelength range. It is possible that the fluorescence of coral polyps is a protective reaction to eliminate harmful ultraviolet radiation. If living organisms on the planet have mastered this method of energy conversion, it could even glow intensely at certain wavelengths, possibly even in the visible range. Such powerful luminescence could be detected even from Earth. It is not surprising that the neighboring and so diverse system sparks immense interest. After all, by cosmic standards, it's within arm's reach. This is precisely why the extraordinary project called Breakthrough Starshot is of considerable interest at the moment. The project's goal is truly fantastic: to send a flotilla of interstellar microships to Proxima Centauri in the coming decades. These miniature probes are even called starships. Don't confuse them with appetizers. It is envisioned that 1,000 or even tens of thousands of such probes, weighing no more than 1 gram, will be delivered to Earth orbit and launched towards Proxima Centauri. The miniature probes will deploy solar sails measuring 4 by 4 meters. The ultra-thin foil will reflect incident radiation, accelerating the flight like a sail inflated by wind. The probes will be propelled by beams from an array of lasers located on Earth. This will be a terrestrial phased array of laser emitters measuring 1 by 1 kilometer. Thus, starships can reach up to 20% of the speed of light. And the flight to Proxima Centauri, if all goes according to plan, will take approximately 25 years. Upon arrival in the Alpha Centauri system, the probes will gather necessary information, photograph the surroundings, the system, and the planets. And 5 years later, this data will need to be received on Earth. These are the plans. In conclusion, it should be noted that climate modeling of Proxima Centauri b yields completely different results depending on numerous parameters: the planet's rotation speed around its axis or its absence, the presence and salinity of water, continental distribution, atmospheric density and composition, and so on. We hope that further study of this planet, as well as the flight of the Starship's interstellar flotilla, will help us definitively ascertain the possibility of life on this planet. Traditionally, we will keep our fingers crossed that the project continues to develop. You can always find more detailed information on our social media and Telegram channel. The link will be in the description. In the meantime, the closest potentially habitable planet to us remains mysterious and completely unreachable. What do you think? Does the enigmatic planet Proxima b have a chance? Or should we search for life in other corners of our galaxy? A stellar journey awaits us. Today, we'll peek into the future, where a unique expedition embarks on a long 10,000-day voyage to the very Tau Ceti. But first, a brief excursion to study the destination station where our starship will arrive. The Tau Ceti system is part of our immediate stellar neighborhood, and sunlight reaches it in 12 years. This system ranks third in distance from the solar system, second only to Alpha Centauri, at a distance of 4.3 light-years, and Epsilon Eridani at a distance of 10.5 light-years. Tau Ceti, however, is separated from Earth by 11.9 light-years. Incidentally, it is visible to the naked eye in the southern hemisphere in the constellation Cetus. It is slightly smaller than the Sun, relatively stable with minor fluctuations in brightness. Its spectrum shows low metallicity, and therefore the presence of giant planets is unlikely in this planetary system. According to exoplanet search results, 4 planets orbit the star with orbital periods of 20, 49, 168, and 642 days. The minimum mass values of the discovered planets are 1.7, 1.8, 3.9, and 3.9 Earth masses, respectively. The closest planets, designated G and H, are of little interest to us as they orbit too close to their star. However, planets E and F are located quite close to the habitable zone. The habitable zone is, of course, a relative concept. The planet's climate strongly depends on its atmosphere. Planet E receives about as much heat as Venus, which might have been habitable before the greenhouse catastrophe occurred. In turn, Planet F receives as much heat as Mars, which was likely suitable for life until it lost almost its entire atmosphere. Planet F is most likely suitable for life. Such a heavy planet should possess a sufficiently thick atmosphere capable of making it more hospitable than early Mars, where rivers once flowed into seas. But Tau Ceti has a mitigating circumstance, although not as fatal as with red dwarfs. Measurements made by the submillimeter interferometer, ALMA, have shown that there is quite a lot of dust around the star. A dust belt extends from 10 to 60 astronomical units. There is an order of magnitude more dust there than in the solar system, and dust itself is seemingly harmless. But where it is, so are asteroids, of which there are also significantly more than ours. This is somewhat like searching for the Kuiper Belt, only denser and closer to the star. But again, unknown circumstances are important here. What is the entropy of the dust belts in this distant system? In other words, how dynamically relaxed is it? How elongated are the orbits? And what is the dispersion? Well, we will find out. There's no time to wait. Let's embark on a long journey. So the year 20,139, day 1. The final destination for our travelers has been chosen. Tau Ceti F, a super-Earth with a confirmed radius twice that of Earth. Considering the planet's mass, the gravitational force for humans is more than acceptable. A dense atmosphere capable of maintaining optimal temperatures for various complex life forms, including humans, has also been confirmed. The asteroid belt does not intersect the planet's orbit. Earth 2.0 has been found, and today we are flying to it. The interstellar spacecraft Star Whale was assembled for several years in Earth orbit from individual modules, delivered by heavy rockets, and placed into high orbit using a reusable orbital tug. For the convenience of builders and residents in orbit, a large orbital station called Family was created. And now, the first colonists are arriving at the Star Whale, built by the efforts of all of humanity on Earth. Their total number is 136 people, of which 68 men and 68 women, aged between 27 and 30 years old. The entire flight to the Tau CT system will take 28 years, or 10,000 days, to ensure comfortable transit and prevent premature aging during the extended voyage. Half of the crew is placed into a state of suspended animation, sleeping for 14 years. Upon awakening, they will relieve their colleagues who have been continuously maintaining operations aboard the vessel. Return to Earth is not part of the mission profile. This is a one-way expedition, with the primary objective being the establishment of the Natukita F settlement colony. It is the 7th day of the journey. 68 crew members are already enclosed in specialized cryopods, inducted into a prolonged state of hibernation. Medical personnel are diligently monitoring the vital signs and overall condition of the sleeping crew. To reach their designated planet within a relatively short time frame of 28 years, a revolutionary deep space vessel was meticulously designed and constructed by various scientific and industrial consortia. This spacecraft is capable of traversing interstellar distances, carrying our colonists ever further from Earth. It is a nuclear pulse propulsion craft, utilizing a magnetic sail for deceleration. The project's foundation lies in the concept of an impulse fusion drive. This system operates by detonating small nuclear charges and reflecting the reaction products with a powerful, high-intensity magnetic field, thereby generating the thrust required to propel the ship forward. A colossal superconducting ring is integrated into the aft section of the starship, generating the precisely configured magnetic mirror. At its focal point, a sustained detonation of a sufficiently powerful fusion charge occurs every 0.2 seconds. The resulting high-temperature plasma and light emission are then reflected by the magnetic mirror, expelling outward as a reactive jet. The starship, affectionately nicknamed Stellar Whale, is projected to achieve its maximum velocity of 150,000 kilometers per hour second within 3 years, which equates to half the speed of light. It is the 35th day. Engineers, physicians, and specialists in fields such as artificial intelligence, genetic engineering, psychology, and many others have completed a comprehensive foundational course on the construction and operation of all ship systems. This is crucial, as in any critical situation, every crew member must be capable of addressing and resolving any unforeseen issue. Presently, a routine diagnostic of the ship's power systems is underway. During flight, These systems are supported by 4 nuclear reactors with extended operational lifespan projections. The Starship carries a sufficient reserve of fissile material to sustain an average of 100 years of travel. 320,000 nuclear charges for the propulsion system are stored within the ship's structure in 8 specialized containers, each equipped with a cooling system and a unique revolver feeding mechanism. Following the acceleration phase, these containers will be jettisoned. The vessel also incorporates defensive measures against residual radiation from the nuclear engines, as well as interstellar radiation and dust, with a total mass of approximately 800 tons. It is the 245th day of the flight. The crew is adjusting the stellar whale's trajectory to enter Saturn's orbit for its initial gravitational maneuver. Within mere days, the awake colonists are graced with an extraordinary spectacle, the breathtaking ringed gas giant. The maneuvers at Saturn are successfully completed, and the ship gains further velocity in the cosmos, leaving behind the diminishing star known as the Sun. Their destination is a similar star, now too distant to ever contemplate a return. It is the 653rd day of the flight. From its maiden voyage, the stellar whale has operated on complete self-sufficiency, as no resupply of consumables is possible. Closed-loop regenerative biotechnological life support systems, relying on physico-chemical processes, maintain optimal living conditions for our colonists. Crew members periodically conduct system checks for oxygen supply, water reclamation, atmospheric purification, temperature and humidity regulation, and numerous other critical functions. This self-contained life support system utilizes waste transformation via aerobic microorganisms, biofilters, and aeration tanks to generate nutrient solutions for photoreactors, cultivating algae and higher plants in the onboard greenhouses. Within several modules of the ship, astronauts cultivate and sustain botanical gardens, which provide essential oxygen and sustenance in the form of greens and vegetables. The closed ecological system functions as follows. A pump within the system blends water from a collection reservoir with biological waste. This mixture is then pulverized in a grinder. Oxygen is introduced, and the mixture passes through a filter composed of red cedar bark fibers, where bacteria and protozoa metabolize a portion of the contained nutrients. Subsequently, the mixture enters an aquarium containing fish, which consume microorganisms deemed detrimental to the ecological balance. After passing through a membrane diffuser, the mixture is purified of toxic impurities and carbon dioxide, and water vapor is separated. The majority of the water is recirculated back into the cycle to the pump. A smaller portion, rich in inorganic nutrients, is periodically directed to the hydroponic greenhouse. The plants within the greenhouse absorb carbon dioxide and release oxygen, which is then returned to the habitable areas. It is the 1216th day of the flight. The colonists aboard the Whale are charting a course toward Neptune, aiming to execute another gravitational maneuver to achieve maximum velocity. Through the ship's portholes, crew members observe the final planet of their native celestial neighborhood, the solar system. Throughout the entire journey, extensive photo and video recording is being conducted, serving both as personal archives and for potential transmission back to Earth. The spaceship is equipped with all necessary provisions, not only for operational tasks, but also for leisure and recreational activities. Psychologists are facilitating dedicated group sessions to foster and maintain a healthy emotional environment on board. It is the 1,300th day of the flight. The requisite velocity for interstellar transit has been achieved, and our stellar whale is now swiftly navigating the cosmic ocean, inexorably closing the vast distances. Meanwhile, the colonists continue their lives and work as before. Several couples are anticipating the arrival of new family members, undergoing more frequent medical checkups to monitor their health. Additionally, the ship features athletic facilities to maintain physical fitness, despite the presence of artificial gravity systems. It is the 1,543rd day of the flight. The first human being has been born in outer space. The mother and infant are in excellent health, a fact immediately communicated to Earth. The colonists experience no scarcity of water or food. In the modules dedicated to agricultural activities, plants and vegetables are successfully being cultivated through aquaponic and hydroponic methods, catering to the growing needs of the increasing crew population. It is the 3,857th day of the flight. The stellar whale boasts a comprehensive library, with its servers containing a vast repository of diverse literature. Several crew members are presently engrossed in reading the works of great classical authors, while others might be immersed in computer simulations, offering a plethora of games and applications. Some engage in meditation, play games like Tetris, converse with fellow crewmates, train their pets, or simply pet their fish. All in all, the living conditions are quite satisfactory. It is the 4,961st day of the flight. The mission of the initial colonists is drawing to a close, and they are commencing the process of awakening the hibernating crew members. Initially, the newly awakened individuals receive assistance with their medical evaluations, help in familiarizing themselves with the ship's operations, and are provided with all essential work-related information. Children born aboard the vessel have been assigned to educational groups, continuing their learning and acquiring knowledge in various disciplines. This curriculum includes a dedicated course on Earth, its history, and its cultural heritage. It is the 6,783rd day of the flight. On board the starship, a variety of three-dimensional printers are available for diverse printing needs, ranging from foodstuffs to essential components and tools required for ongoing repairs. The majority of the complex task of flight control and trajectory correction is delegated to artificial intelligence. The stellar whale operates on full autopilot. Crew members are primarily responsible for monitoring data streams and verifying course coordinates. The artificial intelligence provides instructions for complex operations or repairs, owing to its rapid information retrieval and systematization capabilities. The AI is also utilized for continuous monitoring and tracking of even the slightest changes in crew members' health. This allows for timely intervention and prevention of severe complications. For instance, any crew member can receive advice on how to avoid a headache or alleviate insomnia. Physicians, in conjunction with the artificial intelligence, are successfully managing pregnancies and assisting in childbirth. Beyond its functional roles, the AI also possesses a social dimension, engaging with crew members during their long voyage. To facilitate this, developers have incorporated facial recognition capabilities and simulated human emotions on its display. This allows the AI to recognize sadness and offer support. It is the 9,269th day of the flight. 2 years remain until arrival at the Tau Ceti system. Preparations for the deceleration sequence are commencing. A magnetic sail will be deployed to generate resistance within the interstellar plasma medium. The maneuver is successful, and the crew rejoices. It is the 9,970th day of the flight. 1 month prior to entering orbit around Tau CTF, the hibernating crew members are roused from their cybernetic slumber. During their sleep, the aging process was maximally decelerated. Thus, their age upon arrival does not exceed 44 years. Children born earlier are, on average, between 20 and 23 years old, while those born later range from 8 to 13 years of age. However, this does not constitute the complete population for colonization. Aboard the stellar whale, hundreds of tiny frozen human embryos have remained in stasis throughout the journey, awaiting the opportunity to come to life upon the successful completion of the mission and the establishment of the first colony on the new planet. We have reached Tau Ceti after 10,000 days. The vessel is entering the orbit of a distant planet. No definitive signals have been detected yet. Astonishingly, the data confirms our findings. Water, carbon dioxide, methane, oxygen, and ozone have been detected. All of these are present on the only planet in the Tau Ceti system deemed habitable. It is remarkably similar to Earth. It is possible that the new planet harbors intelligent life, organisms that appear entirely different. Meanwhile, automated probes are being deployed to the planet for territorial exploration, sample collection, and robots are commencing the construction of initial habitats for the settlers. After a period, the first group of individuals descends to their new home within the landing craft, breathing deeply the air, a pleasure to inhale, rejoicing in the warmth of a new sun, and touching the yet unknown new, but remarkably pleasant to the touch vegetation. The colonists celebrate and congratulate each other. The long voyage has truly united people from all walks of life, forging them into the first interstellar family. A splendid conclusion. However, the reality is that events could unfold differently. The most powerful space telescope currently in operation, the James Webb Space Telescope, has been gathering data on the remarkable exoplanet K2-18b. It is approximately twice the size of Earth and resides in a system located 120 light-years away in the constellation Leo. Astronomers are particularly drawn to this planet due to the detection of biosignatures in its atmosphere. On Earth, this compound is primarily produced by phytoplankton in marine environments. Consequently, the discovery of such organic matter in the atmosphere of a distant planet has generated significant interest, leading to the hypothesis that K2-18b might not only harbor marine life, but could also be entirely covered by an ocean, which in turn could generate colossal tsunamis due to its proximity to its star. However, before delving into intriguing details, including the fate of Matthew McConaughey, let us examine precisely how oceanic planets in distant systems come into being. As we understand, ocean planets are a classification of planets composed primarily of ice, rocky materials, and metals. Depending on their distance from their parent star, they can be entirely covered by oceans of liquid water, reaching depths of up to 100 kilometers. The precise depth is contingent upon the planet's radius. At greater depths, the pressure becomes so immense that water can no longer exist in a liquid state and solidifies, forming various ice modifications. If, during the formation of a planetary system, At a considerable distance from its star, a protoplanet attains a mass of approximately 10 Earth's masses. It becomes sufficiently massive to attract hydrogen and helium, ultimately evolving into a gas giant. A planet with a slightly lesser mass, around 6 to 8 Earth masses, and failing to reach the 10 Earth mass threshold, ends up being composed predominantly of ice and rock, akin to the moons of the giant planets in our solar system. If such a planet is, on one hand, massive enough to maintain its own orbit around a star without being captured by a nearby forming gas giant, and, on the other hand, not massive enough to attract hydrogen and helium from the gas and dust cloud in which it is forming, then, in a simplified model, a resulting icy planet is formed, composed approximately half of ice and half of solid rock, rendering it a decidedly cold and somber place, devoid of any semblance of cheer. However, over time, through migration driven by powerful turbulent disturbances within the protoplanetary gas and dust disk, which can alter the planet's orbit, such an icy planet might find itself sufficiently close to its star for the planet's outer icy crust to melt, resulting in the planet becoming completely enveloped by that very ocean of liquid water, with depths ranging from 70 to 140 kilometers. The pressure at the bottom of such an ocean, approximately 15,000 atmospheres, is sufficient to form polymorphic ice modifications that are denser than liquid water and, under such pressure, will never melt. Below this will lie a solid crust of various ice modifications, approximately 5,000 kilometers thick. Finally, there is a solid core with a radius of about 8,000 kilometers, primarily composed of a rocky mantle and metallic elements. Indeed, ocean planets are exceedingly rare, and one could count them on their appendages. Yet, it is precisely such a planet that the newly commissioned James Webb Space Telescope has discovered. And here, we can discuss new details. The planet completes an orbit around the star K2-18 in 33 days and receives 5% more light from it than Earth receives from the Sun. It was previously thought that the planet belonged to the class of gas dwarfs, or mini-Neptunes, which represent an intermediate category between Earth-like planets with solid shells and gas giants like Uranus and Neptune. However, the results of the new research suggest that planet K2-18b is a Hycean. Hyceans are defined as planets entirely covered by water. It is believed that moderate temperatures and conditions conducive to life are maintained on their surfaces. The precise atmospheric composition is still being determined, but it is known to contain hydrogen, helium, carbon dioxide, and methane, much like a young Earth. Therefore, the discovered exoplanet can rightfully be called a water world. The most intriguing finding is the detection of dimethyl sulfide traces. They did not find the compound itself, but rather indicators of its presence. Nevertheless, this is also a highly interesting discovery. On Earth, this organic compound is exclusively released by bacteria, plankton swimming in the water, and certain algae. It is typically emitted by bacteria in wastewater and sewage, contributing to unpleasant odors. However, in low concentrations, this substance imparts a bracing aroma to sea air. But do not hasten to launch your schooners for colonization just yet. The system in which this ocean planet resides has a star unlike our Sun. It is a red dwarf, dimmer and cooler than our star. It irradiates its planet and shines upon it reliably. The planet receives sufficient light and heat, obtaining no less of either than Earth. Since the planet is located within the so-called habitable zone, however, when it comes to red dwarfs, the situation is not entirely straightforward. Red dwarfs are the smallest, most common, and longest-lived stars in the galaxy. Superflares are more prevalent in younger, more active red dwarfs, and their power can be up to 1,000 times greater than that of their older counterparts. These eruptions are significantly more potent than any observed from the Sun, and are highly likely to impact the planet's habitability, at least at a moderate intensity. Such flares indeed possess the capacity to strip planetary atmospheres, but this does not necessarily signify doom for unknown life forms. Furthermore, processes might occur on the exoplanet that replenish its atmosphere. It is undoubtedly a harsh environment, and you are unlikely to encounter a happy flamingo there, but as of now, astronomers are not prepared to declare it sterile. But that is not all. Intense stellar activity affects the tides and internal activity of the ocean planet. This implies that colossal waves could form instantaneously, reaching unimaginable scales. But how large could they be? First, it is essential to understand the distinction between a tsunami and the small waves one encounters on a seashore. The difference between these two types of waves lies not only in their size and height. The most significant distinction of a tsunami from ordinary waves is their origin. Ordinary waves are generated by wind. They are rarely as destructive as tsunamis, although they can cause damage to coastal infrastructure. Typically, the damage is confined to a few meters from the shore. Tsunamis, however, originate far from the coast, generally at a considerable distance. Several causes for tsunami formation have been identified, including underwater earthquakes, volcanic eruptions, and landslides. While the latter rarely result in major tsunamis, one particular landslide caused the highest tsunami in history. Approximately 85% of tsunamis are triggered by underwater earthquakes. It is difficult to believe, but the highest tsunami on record had a height exceeding 460 meters and a speed of around 160 kilometers per hour. This event did not occur in the age of dinosaurs, but just over half a century ago. To be precise, on July 9th, 1958, in Alaska, this tsunami was caused by a landslide. Millions of cubic meters of rock and ice cascaded down mountains approximately 1 kilometer high. This triggered a wave of immense power. Astonishingly, water, which appears so soft and harmless, is deceiving. A cubic meter of seawater, measuring 1 meter by 1 meter, weighs approximately 1 ton. A tsunami carries hundreds of millions of tons of water at speeds exceeding 100 kilometers per hour. Such a wave can be fatal upon initial contact, and the chances of survival without a specialized protective suit are almost nil. This is precisely why planet K2-18b could prove to be a merciless world for us. Yes, for us. However, it possesses the necessary amount of carbon and a sufficient quantity of minerals and elements from the Earth's crust that dissolve in the oceans, thereby sequestering carbon from the atmosphere. These planets, already equipped with ample water, merely need to maintain the circulation of carbon between the atmosphere and the ocean, which, in the correct concentrations, is sufficient to ensure stability. Initial modeling assumed that stars similar to our own were necessary, but the results are also optimistic regarding red dwarf stars. Planets and systems orbiting even volatile red dwarfs are considered promising candidates for the development of life, as these stars, in a sense, are much brighter than our Sun, offering the prospect of life over a far more extended period. According to researchers, the conditions could be applicable to planets orbiting red dwarfs, such as planet K218b. Theoretically, all that is required is a constant stellar illumination. To ascertain this, further in-depth observations are necessary. The James Webb Telescope is currently engaged in this endeavor, employing its infrared sensors that facilitate additional spectral analysis to detect other biosignatures and confirm the presence of organic compounds. Currently, this represents the sole available method for searching for extraterrestrial life in other planetary systems. And perhaps, beneath the depths of the water, a vast, as yet hidden from us, aquatic world awaits.